So this is the ideal gas law. The formula for the ideal gas law is PV equals nRT. When we talk about ideal gases, we talk about gases that are existing. You can kind of think of it like on their best behavior. They are behaving exactly how we would expect a gas to behave. In the real world, most gases are not ideal, but we just use this gas law to solve and predict values. So what I want you to look at is the equation PV equals nRT. If you look to see the difference between the gas law problems, in the gas law problems, the first difference is you have ones and twos. You have initials and you have changes, or you have initials and then after a change. In the ideal gas law, you just have one of each variable. So you're going to have one pressure, one volume, one temperature. The other thing you need to look at is all 4 units are involved: pressure, volume, moles, and temperature. In the gas laws, you only used up to 3. The other unit or units were held constant. So in the ideal gas law, all 4 are changing. So in this equation, the pressure is the P. It can be any unit, and we'll come back to that in a second. The volume has to be measured in liters. The number N moles is the number of moles that can be converted to grams if you have molar mass at the end. R is the gas constant. It is a constant, meaning it's always the same. It always has the same value, except that value depends on the pressure unit. So the pressure can be in any unit. It's just your gas constant, R, has to match whatever unit your pressure is in. And then the temperature, like all gas laws, has to be in Kelvin. So we're going to start here. We're going to do the same technique that we did with gas laws, where we're going to write our values on the left-hand side. It's going to help you to determine that you're going to use ideal gas law instead of one of the other gas laws. So we're going to say a sample of gas is found to occupy a volume of 2.85 liters at 22 degrees Celsius. And again, I'm going to change that to Kelvin right away so I don't forget. So 22 plus 273 is going to give me 295 Kelvin at a pressure of 740 millimeters of mercury, mmHg. How many moles of gas are present? So you're solving for your N in moles. Notice what's not mentioned, R. The ideal gas constant, R, will never be mentioned in the problem. It'll never be talked about. You have to automatically know, as soon as you identify this as an ideal gas law problem, you have to know R has to be involved. And it's pretty easy to identify this as ideal gas law. You have a P, a V, an N, and a T. So you have all 4 variables, and you only have one of each. You don't have a 1 and a 2. So remember that R is going to depend on your value of P. So in this case, your P is mmHg. So your R value is going to be 62.4. That is the value of the gas constant when the pressure is in mmHg. Then I'm just going to write my equation. PV equals nRT. And I'm going to start plugging in. So we have 740 times 2.85. Solving for N. Multiply by 62.4, and then 295. So I'm just going to use my algebra. I'm going to multiply and then divide to get N by itself. And N should be 0.11. And then my unit is going to be moles. Always moles for N. Okay, go on to the next one. If the pressure exerted by a gas at 25 degrees, so there's a temp. Again, right away, I'm going to turn that to Kelvin. It's always good to do that so you don't forget later. So 298 K. In a volume of 0.044 liters, so there's a V, is 3.81 ATM. So the pressure is 3.81. How many moles of gas are present? Again, you're solving for moles. Don't forget the R. It's not discussed. You have to know it's there. In this case, my pressure is in ATM, so that means my R value is 0.0821. It has to match. I have my equation. It's going to look very much like the one we just did because you're solving for N again. So I'm going to do 3.81 times 0.044, solving for n, 0.0821 for R, and then 298 Kelvin. Solving for my n is going to give me 0.007 moles. So remember, I'm just going to multiply through and then divide both sides to get n by itself to solve these problems. And then finally it says determine the Celsius temperature. So it's asking us to solve for T, but remember it stipulates it has to be in Celsius. When the problems do that for gas law problems, you have to first convert it to Kelvin. The answer is going to come out in Kelvin. You subtract 273 to get the answer in Celsius. You only have to do that when the problem specifically asks for the Celsius temperature. So then we have an N, 2.49 moles of gas contained in a 1 liter vessel. Liter is going to measure volume at a pressure of 143 kPa. So again, R is not discussed. You just have to know it's there. R value depends on the pressure value. So in this case, it's kPa. So the R value is 8.314. So then I'm going to use my ideal gas law equation. Plug everything in. 143 times 1 equals 2.49 times 8.314 times T. So I'm going to multiply and divide, use my algebra, and I'm going to get 6.91. Now remember, that is in Kelvin right now. The problem asks for the temperature in Celsius, so I'm going to subtract 273, and I get negative 266 degrees Celsius. The reason why you subtract is this. If you remember, to get Kelvin, you're going to add 273 to the Celsius temperature. So now if you want to get Celsius, you would just move this to the side. So to get degrees Celsius, you do Kelvin minus 273.